Reconstructing Earth's past. Let's take a look at fossils today. We're going to basically look at how fossil and the fossil record can be used to help us really reconstruct and understand what's happened in Earth's past. All right, so the fossil record. The fossil record really gives us a unique perspective and basically a really well preserved set of evidence that we can look at to help us figure out what has happened. So fossilization happens in many different types of ways. It can occur, basically in this case we have a trace fossil where no actual part of the organism is preserved. This would be like a footprint or something trekking through sediment that gets compacted down, preserved. It's still considered a fossil. You can get molds and casts. Here we have some petrified wood where basically dissolved minerals in water replace the organic material of the organism and leaves behind these bright colors and minerals that solidify over time. So that's an example of petrified wood. Here we have some amber where bugs, other organisms can get stuck in tree resin. That resin hardens over time and really does an excellent job of preserving the organisms. And then if we're really lucky, we can get some organism that's either mummified or even freezing. So here's an example. This is a baby woolly mammoth that was discovered a couple years back where it was frozen in a glacier essentially. And these types of fossils, these last three, really preserve the organism really well, right down to the point where if they're frozen you can actually figure out what that organism ate that day it died. So some fascinating way. But looking at all this, the only really important thing that thought that we're going to take into consideration is how all fossils generally can be used to help us look at what has happened. So how can they be used as evidence? So the first concept that comes up is the idea of an index fossil, and I want you to think of this a lot like the index in a book. But instead of pointing us to a specific page, index fossils are going to point to a specific point in geologic time in Earth's history. So here, in order to be considered an index fossil, these four things have to be true. The fossil has to be distinct. Basically, it's easy to identify. You look at it, you can very easily figure out what it was. These organisms also had to be abundant and widespread when they lived on Earth. And they also had to exist for a very short period of time. So if all these four things are true, then that makes it very easy to identify that fossil and very quickly reference that point in time in Earth's geologic history. So here are some examples. Looking back on this is from the USGS, United States Geological Survey, and here's a list of some of the index fossils that are commonly used. You'll notice none of these are dinosaurs. In this sense, very rarely will you ever find index fossils from that era. But basically, all of these fossils, when you look at it, come from the marine environment. They're from aquatic environments, which makes sense because aquatic environments are widespread. They cover roughly 70% of the Earth. So if you're going to have an index fossil, it makes sense that they're most commonly aquatic in nature. All right, so index fossils and the way they can be used. Looking at this, you can still apply the same geologic laws we covered before. So we know in this case, if it's undisturbed sedimentary rock layers, the layers on the bottom are oldest and the layers on top are youngest. So looking at this, the trilobite in this case, number 1, would represent the oldest layers. And as we go up, these fossils represent younger and younger rock layers that formed in later time periods. So going on between these two locations, so we'll call this left location is some set distance away from the right location, and you'll notice that both layers really line up beginning with layer 3, so with this moth-like fossil. So in this case, looking at this, because this index fossil exists in both of these rock layers from one location to the next, we know that these rock layers relative to one another are the same age. And this continues on with 4 in both locations, and then 5 exists in in a layer on the location to the right, but not in a layer on the location to the left. In the left, it jumps straight from 4 to 6. This is an easy way to identify a gap in time by using index fossils like this. Probably the most common and easiest way to identify any type of disconformity. So looking on this, and that's basically one of the ways that index fossils can be used to really easily reference a relative age. And then also looking at this, you'll notice that the location on the left has much younger layers. So 7 and 8 exist here, while not in this area to the right. There could be many reasons. These layers could have just formed at a much later period, or there could have just been less erosion over time. There could be many reasons why those rock layers would be younger. Either way, they're different locations, different environments that have gone through different progressions over time. Okay, and here's the same example that we used earlier when we were looking at unconformities with the gap of 200 million years and how these two fossils could be used to identify this disconformity. Importance of fossils. So fossils can be used generally in 2 different ways. They can provide information about geologic history of the Earth, and basically we can use them to show one of 2 things. You can show change in organisms over time, or you can show how the environment has changed over time. So clues to environmental changes. So the first one, we'll cover this really quickly, kind of brings up the concept of evolution. Looking at evolution, for example, if we looked at our own evolution, it's a common misconception that people believe we evolved from apes, when in fact we did not. So looking at this, here's kind of our own heritage. So starting off with this common ancestor, you can see that a single species sometimes diverges into multiple species, and those species continue to diverge over time. So these are our ancestral species, and you can kind of follow right up the line to our own existence. So these are all the hominids. We are the last remaining of all the hominids. We've outcompeted and outlasted, the last of which were the Neanderthals, which went extinct a couple 100,000 years ago, I want to say. I don't know off the top of my head. So that's one example, and you can also look at how organisms adapt over time. So one of the unique adaptations for our own species is the change in skull size. And basically, we have a much greater capacity for a larger brain. So really kind of hinting at the development of our own intelligence over time. In terms of earth science, we can use fossil evidence to really reconstruct how the environment has changed. And the way we do that is looking at sudden changes in fossil type or the overall abundance in fossils. So let's start with the overall abundance. Let's say we are analyzing fossils in a specific layer of rock, and we're counting and keeping track of all the organisms that existed in that environment that were preserved from that time period. And let's say this is an aquatic environment. Okay, so we're done analyzing that layer, we jump to the next, and we notice that for the most part the same species of organisms still exist in this second aquatic layer, but let's say 40% of the initial organisms from the first layer no longer exist. They went missing from the record. This is one way we could actually look at and identify a major environmental change. So in this case, this has the possibility of being a mass extinction. You could identify that, say, 50% of all organisms went missing at this specific point in time. So that just gives us the ability to identify that, and we can then try to figure out what major environmental change happened in order to cause that mass extinction. The same thing goes from, let's say, looking at like a sudden change in fossil type. So in this case, we were looking at 2 aquatic environments over time. Let's say at a later period in time, as you continue to analyze these rock layers, it switches from an aquatic environment to a terrestrial, so a land-based environment. That's a sudden change, very easy to identify. Basically, you'd be switching from marine organisms to maybe a lot of vegetation, a lot of plant life that would exist on land, and you could very easily identify the boundary between those layers as another major environmental change. These are not necessarily unconformities. This could be done continuously throughout time, but it's just an easy way for us to use fossils to identify when major events or major environmental changes have happened throughout Earth's history. All right. And I'm going to kind of give you an example of how we can use this. We're going to look at the Prince Charles Mountains in Antarctica. It's on the eastern side of Antarctica, just south of Australia. Looking at this, here's a satellite image of it. So we have an ice sheet extending out into this bay area here, and this mountain range that extends back in from the bay, where the glaciers run off and into the ocean. So looking at this area, this is a very, very rugged, very harsh environment. Basically, few organisms are sustained in this environment year-round. Very, very harsh environment. But if we went there today and started looking through the geologic record, you'd be surprised at some of the evidence we can find and what we can figure out from that evidence. So first things first, here's a scientist looking at this rock outcrop, and you notice a very clear boundary in these strata, these sedimentary layers for the most part. And I'm going to highlight this in red right now. But this is essentially coal. Coal forms from a very specific process. Coal is a fossil fuel, so it's the remnants and left basically forms from the decaying organic material from past organisms. In this case, coal forms from decaying plants mainly. So you have some sort of swamp or bog-like area where you have lots and lots of vegetation. Every year that vegetation grows, some of it dies, and that decaying organic matter essentially gets compressed, heated over time, and that continually happens until it gets compressed and turned into coal, which you can see off to the right here. So following this organic plant matter gets compressed over time, here it is, and then again over time until you get that coal. These conditions, in terms of areas you would really expect a lot of coal to form, would happen in areas like Georgia's Okefenokee Swamp. Lots and lots of vegetation, lots of dying organic material below all this, and that over time, if this swamp continues to thrive and produce this much vegetation, you would expect to form lots of coal. So Antarctica actually has tons of coal, and coal you can find globally in lots of polar regions. But so that's one kind of hint in terms of events that have happened in the past in this region. Continuing on, you can also find fossils like this in Antarctica. So the one off to the left is of a famous tree. I forget the name, it slips my mind. But this is also, the same tree is found on other continents and would have been found in a more of a tropical-like region as well. And this other fossil off to the right is fern-like. So again, another indicator that there was lots and lots of vegetation in Antarctica at some point in time. So we can really look at these and again look at the same picture, and at some point in time this was a heavily vegetated area, which is much, much different. So sometime between then and now, Antarctica had to go through a few major environmental changes to get to the point where it is today. This very barren, ice-covered, rugged terrain and environment. So again, that's basic summary of how we can use fossils to really reconstruct and quickly figure out the environmental changes that an area has gone through. This video goes through another example. It's actually an awesome video. They look at and discover whale bones and limestone in Egypt, basically right in the middle of the Saharan desert. and using fossil evidence, they reconstruct and look at all the major environmental changes that the Saharan desert has gone through over the past couple million years. So check this video out. It does a great job of summarizing basically what we just discussed in this presentation. If you have any questions, come see me in class and we can go over it.